Hello everyone, welcome to lecture 13 on Mechanics and Materials 1. This is our second lecture on the topic torsion. We have 4 lectures on torsion, and in this one we cover sections 5.3 and 5.4 corresponding to the 5th chapter of the Hibbeler book. Again, recall the big picture of mechanics and materials that we spoke about previously. What we want to do is to find a relation between deformation and loading. And if you remember, for axial loading, we already solved this problem. So the relation that we found was that delta equals PL over EA. So that is the relation between delta and P. What we want to do in this lecture is to find a relation between the angle of twist, phi, and the torque that we apply, T, for a torsion problem. Before I talk about that, I should mention that usually the torsion problem is important and it's useful when we have power transmissions and we want to design shafts. So for power transmission, usually you have a motor and then you transmit the power from the motor to gears using a shaft, and then we need this torsion problem to design the shaft properly. That's what we want to do. Now the power could be generated by electric motors or combustion engines and others, but the idea is that we want to design shafts. So we need to learn also how to convert power to something like torque so that we can later use it for shaft design. In order to do that, all you have to do is to remember that shafts transmit power via rotation. And if you think of power P, that's the rate of work. So it's dW over dt. And basically for a torsion problem, for a rotational problem, dW would be torque times d theta. This is analogous to what you would have for a usual force displacement problem, that dW is F dx. So for a usual problem, dW is force times displacement. So you have Newton for force and meter for displacement. Now you have Newton meter for torque, and then the change of angle is dimensionless, obviously. So this is how power is connected to torque. And when you insert that formula, you can then get this. So P would be T d theta divided by dt. Now, d theta divided by dt itself, it's essentially a rotational velocity. It's an angular velocity. We call that omega, and it has the unit radian per second. So you can write P equals T omega. Alternatively, you can also write that as 2 pi ft, in which f is the frequency and its unit is hertz. It's cycle per second essentially, or 1 per second. And then obviously the relation between omega and f is omega equals 2 pi f. Okay, so this is all you have to know for the relation between power and t. But now, based on what we have learned before, we can also learn how to design a shaft based on what we have just now. Previously, we learned that shear stress, tau, is equal TR over J. So this is what we learned in the previous lecture. Now you can calculate that T from your power by just dividing power by angular velocity. And that's how you can design a shaft. So as engineers, you usually are interested in maximum stress. So tau max would be T, torque, times R max. R max, we show it by the letter C, divided by J, and J was polar moment of inertia. Now, if you reorder these terms, you may also express it like this. So you can say T is equal to max J over C. And then again, for design, tau max is usually the maximum allowable stress that you have, and you can also calculate that from failure stress divided by safety factor. If you order this relation again, then you have also a simpler form. It's T divided by tau max equals J divided by C. The first exercise in this lecture is similar to problem 5.4 on page 193 of the book. The solid steel shaft AB shown in the figure transmits 3750 watt from the motor M to which it is attached. So you have the motor here, motor M, with the power 3750 watt, and the shaft AB attached to that transmits the power from motor to the gear or to the pulley here. If the shaft rotates at angular velocity 175 rpm and still has the allowable shear stress of 100 megapascal, determine the required shaft diameter. So essentially, you are asked how thick the shaft should be such that it can carry enough power. So it can carry the power it's given for the angular velocity that's also given. So to solve this problem, the first thing you need to do is to pay attention that the angular velocity is given in terms of RPM. And what you must do is to express the angular velocity in terms of radian per second. So you need to change the unit of that. In order to do that, you just write that as 175 revolution per minute. And then 1 minute is 60 seconds. So it's basically multiplying it by a 1. And then this is multiplying it by another 1. So 2 pi radian is 1 revolution. So if you do that, then minute cancels with minute, revolution cancels with revolution. So you get 175 times 2 pi divided by 60 radian per second, which is 18.33 radian per second. Okay, so this is your angular velocity. Now you remember the formula we had between power and angular velocity is that power P is equal T times angular velocity. And then again, it's important to pay attention that if power is expressed in terms of watt, then angular velocity must be expressed in terms of radian per second. So that's the reason we did the transformation of the unit for angular velocity. And if you calculate T from this formula, then T, the torque in the shaft, would be 204.6 Newton meter. Okay, now that you have the torque in the shaft, you can calculate its diameter by the relation that we had between the torque and allowable stress. So if you remember, we said the ratio of torque divided by allowable shear stress is the same as J divided by C, and J being the polar moment of inertia. And in this case, it's a solid shaft, so the formula for J is pi over 2C to the power of 4, and C is the maximum radius. The allowable shear stress is 100 megapascal. And from that, you can calculate C or multiply that by 2 to get the diameter. So the diameter is almost 22 millimeter. That's what you wanted to calculate for this question. All right, so let's go back to the first question of this lecture, and that was our motivation for the previous step. We want to calculate the angle of twist. And then again, from the previous lecture, you remember that if you have a shaft before the formation, and let's say before the formation, the lines are straight, and then after the formation, the lines remain also straight, but they get twisted. So if you apply a torque T, this would be your configuration after the formation, and this is before the formation. Now, if I enlarge that picture a little and I show the line before the formation and that longitudinal line after the formation, between those two lines you have an angle gamma, which we also learned that gamma is exactly shear strain. And then you have also this angle here, let's say on the cross-sectional area, that we call that angle of twist phi. And also we learned that angle of twist phi is a function of x, so it will change with x, as you can see. But gamma is not a function of x, so shear strain is only a function of radius. So as you can see here, gamma is the same for every x, but if you cut, let's say, deeper inside the material, gamma gets smaller, and then you can imagine at the center gamma is 0, so when radius is 0, gamma is 0, and also here when x is 0, phi is 0. Okay, but the question is, what is phi x? In order to solve that question, we looked into these little incremental areas, and then based on that, we calculated this relation. So we learned that gamma is equal r times d phi divided by dx, and then d phi divided by dx, it was constant by assumption because we assume that these lines remain straight. And when you know that's constant, then that means d phi divided by dx is the same as phi divided by L, and phi being the angle of twist, or let's say phi at L at the end. Okay, so keep that in mind. The next thing we want to do is to calculate shear stress based on that. Now, shear stress tau is shear modulus G times shear strain. And if you just reorder that, that means shear strain gamma is shear stress tau divided by G. So gamma is tau divided by G. From the two relations, you can also get this one. So let's say from the first relation, you can see gamma is equal r d phi over dx, and then d phi over dx is the same as phi over L. So if you do that, basically from this relation, you know that gamma is equal r phi divided by L. So you know that, and then here you know gamma is equal tau divided by G. And from these two relations, basically, if you equate them, then you get rid of gamma. You get rid of shear strain itself, and you get this relation. So tau divided by G is R phi divided by L. As we will see, this is a key relation for us to find a connection between phi and T. In order to do that, then you should also just connect the shear stress to torque. So if you remember from the previous lecture, and also we talked about it in the first half of this lecture, tau shear stress is TR divided by J. So you have a relation here between shear stress and phi. You have a relation here between shear stress and torque. And basically you can imagine if you combine these two, you can cancel the shear stress itself, and then you can get a relation between torque and phi, the angle of twist, and that's exactly what you want to do. So from this relation, inserting it into this relation, you get TR divided by GJ is equal R phi divided by L. So basically what we have done here is to divide this relation by G and then using R phi divided by L instead of tau divided by G. Then you can cancel R from both sides and basically you are there. You get your relation that we were looking for. Phi, angle of twist, is T times L divided by GJ. And before I go further, I want to remind you that if it was an axial loading problem, the corresponding relation would have been delta equals PL over EA. So now it's phi equals TL over GJ. So this is the angle of twist at the length L, but as we spoke before, phi is a function of x and it is linearly dependent on x. Or let's say because you know d phi over dx is constant, you can imagine that phi x divided by x is the same as phi L divided by L. In other words, once you have phi at L, you can also calculate phi at x. So phi at x, the angle of twist at the distance x from the base, would be tx divided by gj. Now, if we put these two problems of torsion and axial loading one-to-one, let's say on the two sides of the paper, we can see a very interesting analogy between the two problems. So remember, again, in the sense of a big picture of mechanics that we had before, we have deformation, loading, stress, strain. Now, for axial loading, these quantities are delta, p, sigma, epsilon. For a torsion problem, the analogous quantities are phi, t, tau, gamma. So basically, instead of normal strain in an axial loading, you have shear strain. Instead of shear stress in a torsion, you have normal stress in axial loading. So the left problem, the torsion problem, looks like a shear problem. So you have shear stress, shear strain, you have shear modulus, okay? Here you have normal stress, normal strain, elastic modulus, Young's modulus. Now L is the same, length is the length of the member, but the corresponding quantity to area, for instance, would be J. So for axial loading, we divide it by A, and here you divide by J. So J in a torsion problem, it plays the same role as A in an axial loading problem. Torque in a torsion problem is playing the same role as normal force P in an axial loading problem. And finally, the deformation type, phi, angle, is corresponding to delta in an axial loading problem. Okay, so we know that angle of twist is TL over GJ, and that is angle of twist at L, and for x we have phi x equals Tx divided by GJ. Now what about composite shafts? If you have a composite shaft as shown in the figure, so let's say you have a shaft, it has part 1 and part 2, and then you apply a torque TA and TB. We want to calculate the angle of twist. Now, angle of twist here is the angle of twist at A, so you want to know how much it turns. And then because it is fixed at C, you can say phi at A is the same as phi of A with respect to C. And then phi of A with respect to C is the same as phi of A with respect to B, and then B with respect to C. So basically, you calculate how much rotation or how much twist you get from A to B, and then how much twist you get from B to C. You add them up, and you get the total twist at A. Now from A to B, the angle of twist is following this formula, TL over GJ, whereas now T is T2, L2, G2, J2. So it's T, L, G, and J in part 2. From B to C, it's TL over GJ, but now you get this subscript 1 for all the quantities. It's exactly as similar as we did for axial loading. The important thing that you need to pay attention to is that in this formula, when you talk about T2 and T1, and then again, it's exactly similar to axial loading, by the way, T2 and T1, these are internal torques. So you need to cut the structure, you need to calculate the internal torque, and you need to insert that value into this formula to calculate the angle of twist. These are not external torques. Now, if you cut the structure somewhere here in part 2, internal torque T2, it happens to be TA. So you can calculate that from the balance of moments with respect to, let's say, x-axis, assuming that this is your x-axis. But now if you cut it somewhere here, then torque, the internal torque in part 1 is TA minus TB. Again, TA and TB, these are external. And T1 and T2 are internal. Okay, so these are internal as opposed to T1, TA and TB that are external. And then obviously we always need to define a sort of convention for what is positive or what is plus. And our common understanding is that we assume that for external forces, again, this is for external ones, if this is your axis, counterclockwise with respect to that is your plus sign. Okay, and if you do that, then you basically assume that TA is plus and TB is minus because of that. But these are again external. For internal ones, we need to make a better convention or better assumption, and we will talk about that shortly. Before that, let's just sort of summarize this. So if you have a composite shaft, total angle of twist is the sum of TL over GJ over all the parts. Let's say you have n parts, I runs from 1 to n. So you get TL over GJ, and then each of the components, it would be the corresponding value for that part A. But also you can sort of extend that to continuously variable shafts, and if that's the problem, then your phi, the angle of twist, would be the integral from 0 to L Tx dx divided by gx jx. Okay, so you have everything that you need to know for angle of twist, and from that you can solve the problems that come forward in this sort of scenarios. But what we want to do before that is to define a proper convention for internal torques, for the positive internal torque. And we do that by an example here. So let's say you have this example and we want to calculate the angle of twist. For simplicity, it's basically a composite shaft if you want, but for simplicity, you can assume that it's the same shaft. So it has the same area, it has the same cross section, it has the same material. So we are more interested about the signs of the torques and how to handle them. The first thing you need to do is to pay attention that whatever you see on the picture, these are external torques. So for external torques, it's easy. You just assume, let's say this is your longitudinal axis. Let's say it's x direction. And if you assume that, this would be your counterclockwise rotation, and that would be your plus sign. So for external ones, we just assume this plus is counterclockwise. That means you get plus 80 minus 150 plus 60 plus 10, which makes sense because now if you add 10, 60, and 80, you get 150. So this is your balance of torque or balance of external moments. So the member is in equilibrium. That's all good. Now what we want to do is to calculate the angle of twist from A to D. So we want to know what is phi A with respect to D. As I mentioned, if you assume this is the plus direction or plus convention for external loads, now you need to extend that for internal torques. For internal torques, we assume that this combination is our plus convention. Okay? So basically that means if this is your axis X, on the left side it should be counterclockwise. On the right side, it should be clockwise. Again, you can assume that what you get on the left and right, they should be in opposite directions because they need to cancel each other. But then basically, depending on how you cut it, you can assume that it's positive. It's exactly the same thing as we did for truss members. We said, let's say if you have a truss member like this, you need two forces in opposite directions on two ends. But if the member is under, let's say, extension or tension, it's a plus. This is exactly what we do here. So if we calculate the angle of, let's say, point, let's call this point P and point Q. If you calculate the angle of P with respect to Q and you get a counterclockwise rotation from P with respect to Q, that would correspond to something like extension in an axial loading. So this is your plus sign. Another way of looking at it is that if you look at this problem from here, so let's say this is your perspective. So if you look from this side, this would be counterclockwise. If you look from the backwards, now this is also counterclockwise. Okay, so basically you can either memorize it like this or like the other way that I mentioned. But important thing is that you need to remain consistent. Okay, so what we want to do is to calculate phi A with respect to D, and that is phi A with respect to B, B with respect to C, C respect to D. You just add them up and you get this one. And then again, for each of these parts, you can calculate that twist angle for that particular part from our formula TL over GJ, but you just particularize it with respect to that particular section. So it would be TAB, LAB divided by GAB, JAB, and so on. And then again, for simplicity in this example, you may imagine that these are the same, but they don't have to be the same. So the way I'm writing it is just generic. Okay, and then as always, in order to calculate the internal torques, it's a very good idea to draw this sort of graph. So you would just draw the internal torque, and then again, the vertical axis is internal torque. So if you plot the internal torque with respect to, let's say, positions, you can see from A to B, the internal torque is 80, and that's plus 80 because again, if you kind of cut it like that, here you have an external torque 80. So in order to cancel that, on the other side, you would need 80 kilonewton, which looks like this. And according to our convention, that would be a plus. So this is plus 80 Then you apply 150, and then again, if you cut it somewhere here and you play the same game, you write the balance of moments, you get minus 70 here. Then you do the same, you cut it here and you get minus 10 here. You could also obviously cut it from the other side. So if you cut it from the other side, if you just look at that member that we cut, you can see that the external one is counterclockwise, so it's like that. So basically now you would need a moment which looks like this. Let's say it looks clockwise in this direction, and then this is opposite to what we have here. So that would be a minus 10. So this is minus, minus, plus, and that's all you need for this formula. So you insert plus 80 here, minus 70 here, minus 10 here, and then you can calculate the angle of twist. Exercise 2 of this lecture is similar to problem 5.5 on page 209 of the book. The gears attached to the steel shaft are subjected to the torques shown in the figure. So you have the shaft, you have 3 gears on it, and on each gear you apply an external torque as shown in the figure. Determine the displacement of the tooth P on gear A. So here it's point P or tooth P on gear A. We want to know under this loading how much displacement it gets. So it doesn't ask you for angle, it asks you for actually a displacement of a point. The shaft turns freely within the bearings, within the bearing at B. So you have a bearing at B and it doesn't apply any torque as usually we expect it from bearings. The shear modulus of the shaft is 80 gigapascal and its diameter is 14 millimeter. All right, so what you need to do is to do exactly what we did with the previous example and what we learned to do with composite shafts. In order to handle these problems, you need to cut the shaft into different parts to calculate the internal torques for different parts. And then again, the best way of doing that, or to make sure that you don't make mistakes, is to use a graph like this. And then again, on this graph, the vertical axis is internal torque. So if you do that, you cut it somewhere between A and C. And then again, bearing B does not apply any torque, so we can just omit it from the picture. If you cut it somewhere there, and then you remember our convention, and this is our internal moment convention. If you do that, then you can see that on this end, this is your external end. So you have this 150. So your internal end would be here. And in order to have equilibrium for this section, you need 150 Newton in that direction. So that is a plus 150 Newton meter. So plus 150 Newton meter would be the torque from A to C. Then you continue this, you go further and you now cut it somewhere between C and D. If you cut it somewhere between C and D, and then again you just look at it in terms of this picture, so this is your internal moment, and these are external. You need to find equilibrium between them. And obviously you can imagine that you need 130 Newton meter in the direction shown. And if you compare that direction with our convention, you see that it's opposite to what we expected to have. So it's minus. So you get a minus 130 Newton meter from C to D. Then you do the same thing. You cut it somewhere between B and E. And then again, you write the sum of moments with respect to x0 for that part. Now in that picture, again, this would be plus 150 minus 280 minus 40. So you would need 170 Newton meter in that direction, which again, if you look at it from an external perspective, so if you think that's an external moment, that looks counterclockwise, so that should be positive, but it's not, because it is the opposite of what we have here on the convention that we assume. So it's on the other side. So that's minus 170 Newton meter. Obviously, you could have done this also from the other end, but I will not do that. But anyway, you now have the distribution of torques, and that is possibly the most important part of this question. And if you get that right, the next step is fairly standard, because what you can do now is to use this graph. So you know from A to C is plus 150 Newton meter, C to D minus 130, D to E minus 170 Newton meter. So all you have to do is to calculate phi A, which is phi A with respect to C, plus C with respect to D, plus D with respect to E. And then again, we know E is fixed, so phi A with respect to E is the same as phi A, because E is fixed. And then for each part, you use the formula TL over GJ. But then again, you particularize that formula with respect to each section. So it would be TAC LAC divided by GAC JAC. But because all the parts in the shaft, they have the same property, the same mechanical property and the same area, they all have the same G and J. And J is just the polar moment of inertia for the shaft. You can calculate it as pi over 2 times c to the power of 4. You know what the diameter is, so instead of c, we use d divided by 2. So c to the power of 4 would be d to the power of 4 divided by 16. And again, d is 14 millimeter. If you insert that, you get j equals 3.77 times 10 to the power of minus 9 meter to the power of 4. Okay, so you know what is J? G is also given in the description. G is 80 gigapascal. You have the length of AC, CD, and DE. It's 0.4, 0.3, 0.5 meter respectively. And then you have TAC, TCD, and TDE here. So if you insert all that, you can calculate the angle of twist at A. So that's minus 0.2121 radian. And minus indicates that it goes in the clockwise direction. So remember, for external torque or external angle of twist, we assume this is the plus direction. This is counterclockwise. So minus, it means that you get a rotation that is in the opposite direction. But the question asks you what is the displacement of point P or tooth P. So the displacement of point P is the angle of twist times radius. So you basically want to know the arc length at the outer edge of the gear. So you multiply the angle of twist that you calculated here times radius. So this would be 21.2 millimeter. And then again, it basically means it comes in this direction. Okay, so you get 21.2 millimeter as the displacement of point P. Exercise 3 is similar to problem 5.7 on page 211 of the book. The 0.05 meter diameter solid post with shear modulus 40 gigapascal is buried 0.6 meter in soil. Okay, so this is the post and it's buried at its bottom part, which is 60 centimeters. A torque is applied on top using a rigid wrench. So you apply a torque on top here. Let's say you have a wrench and you apply 100 Newton on each side. So this whole structure, this gives you a couple. It gives you a torque. Determine maximum shear stress in the post, angle of twist at its top. Assume that the soil exerts uniform torsional resistance and the torque is about to turn the post. Okay, so the torque that we apply is about to turn it, but it's not yet turning it. It's just before that. And also the resistance that you get at the soil, it's a uniform distribution. So it's a load with the density, or it's a torque with a density T. Okay, so T is sort of torque per meter if you want. Okay, so again, for all these problems, possibly the most important thing is to be careful about directions, about rotations, and so on. So we need to define a proper coordinate system. So let's assume that the coordinate system starts at the bottom. So that would be our x-axis, that longitudinal axis. So it looks like we are looking at it from top then, and this is exactly your longitudinal axis. Now, if you think of your torque, you apply a counterclockwise rotation on top. So assuming that is the plus direction for x-axis, this would be counterclockwise and also plus. Okay, so that's the torque you apply on top, and then from A to B, the torque is constant, but then gradually it will reduce to basically 0. If we want to draw the distribution of the internal torque, so this is exactly the similar graph that we had before. So now if you want to draw internal torque, and internal torque, again, this is what we usually call capital T. From B to A, you just get plus 30 Newton meter. And then again, 30 is essentially 2 times 100 times 0.15. Okay, so this is the torque that you get from the wrench here. So from A to B, you get a constant torque. And then from B to C, you have a torque distribution, and that is something like torque per meter if you want. So you have that torque distribution T, and that means what you get is an integral of that distributed torque over the length. But also from equilibrium, you know that at the bottom, you have no additional torque to the system. So at point C, you know that torque is eventually 0. Okay? So this is what you know. Again, on point A, you can imagine the same thing. So basically, the jump that you get here is the jump that you would cancel out with the external torque that you apply. But because at the bottom, at point C, you get no additional torque, then T should be 0 at point C. But then because we also know that the distribution is uniform, it's said by the example, it means you have a uniform line, or a line with a constant slope. Okay, so From C to B, it could be anything in principle, but it tells you clearly that T is constant, and T is exactly the slope of that line in a way. Okay, so if you think of torque between C and B, or from B to C, the equation for that long line is Tx plus Tc. So it's usual relation like y equals mx plus b. But we know b is 0 because it's equilibrium at C. So you don't have an external torque at C. And that means TBC, the line equation is just Tx. And then you also know that if x is 0.6 meter, so if you reach point B, you should get 30 Newton meter for the torque. From that, you can calculate the slope of the line T, which we know it's constant. We don't know what is the constant. We don't know its value, but we know it's constant by problem definition. So T is 50 Newton meter per meter. Okay, so now you have almost everything you need. You have the torque distribution, the internal torque distribution. And I think, again, this is possibly the most important part of this question. Once you have that internal torque distribution, you can integrate it from, let's say, x0 to L to calculate the angle of twist or anything else that you want. So the question before asking you about the angle of twist, it asks you about maximum shear stress. So you can see that shear stress formula is Tc divided by J. Or again, you remember our formula was tau equals Tr divided by J. Now, if R is R max, you get the tau max, and R max is what we just call C. So Tc divided by J, that gives you the maximum shear stress, and C and J are constant for the post. So basically, you get maximum shear stress where T is maximum. Now, where is T maximum? T is maximum at any point between A and B. So it's constant, but the maximum value of T is actually 30. So you insert that. So you insert 30 here, you insert C and J is, again, it's a solid shaft, so it's pi over 2 C to the power of 4. So you get the maximum shear stress of 1.222 megapascal. So that's what the question asked first, and then for the angle of twist, at A, again, you can say, because at C, you know the angle of twist at C is 0, because the problem tells you the shaft is about to turn. It actually tells you it's not turning yet, so phi at C is 0. So phi A, or the angle of twist at A, is exactly the same as phi of A with respect to C. And phi of A with respect to C is phi of A with respect to B, and B with respect to C. And in order to do that, then we use the formula we had. From A to B, it's constant. So you can just say it's TL over GJ. TAB, LAB, GJ. GJ is the same throughout. But from C to B, or if you say, again, B with respect to C is the same as from C to B, then you integrate actually from C to B of TBC dx GJ. Pay attention that I'm just calling it TBC in a sort of sloppy manner. Maybe you want to call it TCB to be more clear that you're talking about the direction from C to B, but it doesn't matter. We know what we are talking about. We are talking about the line between C and B, okay? And this is the slope that it has. So the slope is plus 50, as if we go from C to B. Okay, so Now, for TBC, you just insert this. For TAB, you just insert this. And if you do that, you can calculate the angle of twist at A, and that would be 0.0015 radian. So this is a very, very interesting problem. And as you can see, you sort of see a combination of two types of problems. You see sort of this thing that we had for composite shafts, and then you have this part that we saw for, let's say, continuously changing shafts. Then you add them up to get an answer for the problem. All right, so this was our second lecture on the topic torsion, and we covered sections 5.3 and 5.4 of the chapter 5 of the Hibbeler book. As I mentioned before, we have 4 lectures on torsion. That means we have 2 more of them to come. So we have torsion 3 and torsion 4 to come later. I'll catch you in the next one.